Now this time, we're going to take an alternative viewpoint toward the implicit differentiation. Previously, we started off from an implicit relationship between x and y, kind of like this. And then we took the derivative implicitly, kind of like this, regarding x as the independent variable and y as dependent. Consequently, by chain rule, we have y prime popping up whenever we use the derivative formula with respect to y. Now this is when x is independent and y is dependent. Now why not both of them to be dependent with respect to another variable, say t? Typically t is for time. In that case, both x and y are functions. So we're going to get primes popping out for both of them, like this. Color-coded, x prime is blue and y prime is red. Please note, this x prime came from x cubed, taking the derivative 3x squared, and then x prime popped out because x is no longer independent, it's dependent. And this x prime and this y prime, those came from product rule, and this y prime that came from the chain rule. Here is the theoretical background. We have functions of t like this, and then by chain rule we have to multiply the derivative of the inside, and then in the middle those are from the product rule. In short, we're going to have primes everywhere, and that's an implicit differentiation too, and we don't have separate name for that. It's just another aspect of implicit differentiation when both variables are dependent. Or if you have z or uv's or even more variables, you can make all of them dependent with respect to time t. And that kind of implicit differentiation is something we're going to study here. And here's an example. Related rates. Why related rates? Because these rates, x prime and y prime, are related to each other. Here we go. Here's an example. We have an implicit relation, the same relation we saw before. X cubed plus xy plus y cubed is equal to 1. And here's the problem. X equals to 1 and y prime is negative 1, and we have to find out y and x prime. Basically, we have this kind of situation. So x is equal to 1, we know, and x prime, we don't know that. Y is equal to, no, we don't know that. Y prime is equal to negative 1. This situation. We have two functions, x and y. So we have those two functions and two variables, x prime and y prime. But then again, among those four quantities, x equals to 1 and y prime equals to negative 1, those two are known. And the other two, x prime and y, are unknown. So in short, we have to find out these two unknowns with this one equation. That doesn't look good. If you have two unknowns, we had better have the second equation. How do we get the second equation? Of course, we can do it by implicit differentiation. 3x squared x prime plus x prime y plus xy prime plus 3y squared y prime is equal to 0. We have equation number 1, original, equation number 2 from implicit differentiation, and then two unknowns, x prime and y. Plug in the other as numbers in, and can we solve the system of equations, system of nonlinear equations, two equations and two unknowns? Yes, that's going to be possible. It may be a bit of a challenge, but it is possible, and this kind of process is called problems related to problems on related rates. X prime and y prime are both rate, and they're related. Here's the solution. We have equation number 1, the original, and equation number 2, the implicit differentiation. Now here, let's plug in numbers. X is equal to 1 and y prime is equal to negative 1. Plug in x equals 1 there, and then x equals 1 and y prime equals a negative 1 there. Then you're going to get equations 1 and 2. And they're like this. First equation. Plug in x equals to 1. 1 cubed plus 1y plus y cubed is equal to 1. And please note this 1 and this 1 cubed, they cancel each other out. And this is what we get in the end. Y plus y cubed is equal to 0. Do you see? From here, plug in x equals to 1. So 1 cubed plus 1y plus y cubed is equal to 1. And this one and that one cancel out. And this is what you get. Y plus y cubed is equal to 0. Luckily, this is relatively simple equation to solve. You can factor and then set it equal to 0 here, y equal to 0. The other, 1 plus y squared, will never become 0, so we get y equal to 0. We wanted to find out y value and x prime. One of the two is done now. Y is equal to 0. Now we'll have to use the other equation. From here, plug in x equals to 1, y prime is negative 1, and also y is equal to 0. And the only unknown here is x prime, and we can algebraically solve it. Here we go. Plug in all those numbers in, and then we had x prime is equal to 1/3. So we have y equal to 0 and x prime equals to 1/3. Now, are you ready for more applications? Okay, let's go. Now these problems are word problems, but they're all related rates. We have two or more variables put together as an implicit relation, and we have to find out the next equation through implicit differentiation. For some numbers, we'll have to solve a system of two equations with two unknowns. Problem number 1 here. If a snowball melts so that the surface area decreases at the rate of 1 cubic centimeters per minute, find the rate at which the radius decreases. So we need to find out the relationship between the surface area and the radius. Here it is. S equals to 4 pi r squared. This is the surface area formula. Now if you take the derivative, this is what you get. F prime of t is 4 pi and 2r and then r prime. If you prefer to use Leibniz notation, then you can write like this: ds dt, and then this one dr dt. The equivalent. Here in this notebook, I'd prefer to use prime notation a little bit more, so let's just go back to the original here. So from here, we took the derivative implicitly. Now what more do we need? We need, let's see, s prime is negative 1 and r is equal to 5. And from that, we have to find out s value and an r prime value, eventually r prime, because we have to find the rate at which radius decreases. So r prime is the quantity that we have to find out eventually. So how do we do that? Well, here's the solution. Here is the surface area formula. We take the derivative implicitly. S prime is equal to 8 pi r, r prime, 4 pi, and then also 2r, so we have 8 pi. We have these two equations, and then we can find out s and r prime value by plugging in those numbers. S prime is negative 1, and we are using negative because decreasing. R is equal to 5 centimeter. So S, if you plug in everything here, you're going to get 4 pi times 5 squared. So 4 times 25, that's 100 pi. So we get this surface area for the moment. But unfortunately, this is not the part of the answer that problem is asking you to do. The problem is asking you to find out the rate at which radius decreases. So we want r prime. So we need the second equation here. So S prime is -1 and then r is 5. Just run your computation in. -1 is equal to 8 pi times 5. So r prime is -1 over 40 pi. Run your calculator and this is what you get. -0.008 centimeter per minute, approximately speaking.